So in some of the examples that we've seen up until now, we've seen that water can act as either an acid or a base. Sometimes it donates hydrogen ions, and sometimes it accepts hydrogen ions. And on top of that, sometimes water can react with itself and produce hydroxide ions and H3O+, the hydronium ion. But we often simplify this kind of reaction a little bit. And we can write an equilibrium expression for this second reaction. Remember that because water is a liquid, it doesn't show up in the equilibrium expression. And because the coefficients on each of these ions are 1, the exponents are also 1. This equilibrium value, this K, is known as the ion product constant for water, and it's given the symbol Kw. And at 25 degrees Celsius, Kw for this reaction is 1 times 10 to the minus 14. And what this means is, in any sample of water at 25 degrees Celsius that's at equilibrium, you're going to have H plus ion concentration and OH minus concentration being equal and multiplying to give you 1 times 10 to the minus 14. And those ion concentrations, because they're equal, both need to be 1 times 10 to the minus 7 molar. So a sample of pure water at 25 Celsius, where the ion concentrations are 1 times 10 to the minus 7 molar, with these conditions, you have a situation that's known as neutral. And then if you shift these concentrations by adding either an acid or a base, the concentrations will no longer be equal, and you're going to have either an acidic or a basic solution. So in a situation where your H plus ion concentration is larger than your OH minus concentration, you have more H pluses than OH minus, you have an acidic solution. And then when you have more OH minus and less H plus, you have a basic solution. And the thing that makes this so useful and important is that it's true for water, and it's also effectively true for aqueous solutions. Although an aqueous solution is going to have other ions and things in the solution, their effects are often negligible, so that most of the time we only ever need to consider H plus ion concentration and OH minus ion concentration. So no matter if you add acid or base to water, effectively what you're doing is just changing the position of the autoionization equilibrium. Kw is always equal to H plus times OH minus equals 1 times 10 to the minus 14. If you add an acid to water, think about what happens. Inside any neutral sample of water, you have liquid water, and you have a small amount of H plus ion and OH minus ion. If you add acid to water, you're going to use up some of the OH minus ions, because they will react with the incoming H plus. And if you use up some of that hydroxide ion, its concentration goes down. And Le Chatelier's principle says that if you decrease the concentration of one of the products, the reaction will shift to produce more of them. And that means you end up with a situation where more water autoionizes to make H plus and OH minus. And you'll end up with slightly more H plus and slightly less OH minus. But no matter what, the product of those two concentrations are going to equal 1 times 10 to the minus 14, because the equilibrium for water is still true. And the same kind of thing is going to be true if you add a base to water. Some of the H plus ions will be used up, and then the equilibrium will shift to produce more H plus and OH minus, leaving you with a situation where you have slightly more OH minus and slightly less H plus. But again, the product of those two values will be equal to 1 times 10 to the minus 14.